Our speaker today is John Rehr, now an emeritus professor at the University of Washington, adjunct professor at SLAC. His group is well known for the development of X-ray spectroscopy theory and the FEFF code. Today's talk will review advances in the theory of XAS with applications to a number of spectra as implemented in the recent release of FEFF 10. All right, John.
Okay, I hope everyone can hear me. Good morning or afternoon or whatever time zone you're in. I'm very happy to be here today. And I want to say that the talk has a little bit of very old stuff, a little bit of medium old stuff, and some new stuff. It's also similar to a talk that I gave last week, but shortened. So if you were there, maybe this is repetitive. Anyway, with that, you've seen the title and you've seen the Feynman diagram, which is basically summarizes the theory that I'm going to discuss. Briefly, I'm going to talk about advances in the theory over the past few decades. I'll start with a review. This is, of course, very old, but it's always nice to do a little review of the theory. And I'll try to focus on some of the physical considerations that were involved. Then we'll transition to a discussion of some related spectra that are similar to X-ray absorption, electron energy loss, resonant inelastic X-ray scattering, and so on. And then in the last part, I'll discuss our recent work on including many body effects, satellites, and the high temperature extension up to the warm, dense matter regime. Okay, so briefly, what do we want to do? I've shown on this plot the X-ray absorption spectrum. In this case, it's aluminum. It's aluminum metal and face-centered cubic phase. And I've plotted the absorption, which you can see goes over about 10 decades, from the ultraviolet to hard X-ray energies, that is about 1 EV to about 10,000 EVs of photon energy. And it's interesting, what you see is that there's a steady decrease with maybe not so steady jumps, some down, some up, as you go up in energy. And these jumps reflect the inner shell structure of the aluminum atom. Down here, there's the inner core, like the 1s, and then there's 2s, 2p, et cetera, and finally you get down to the valence or continuum spectrum with very low energies. But if you look closely and zero in on one of these so-called X-ray edges, the edges occur at energies just sufficient to knock an electron out of the core. This is Einstein's famous photoelectric effect. But if you look very closely, you see a whole bunch of structure wiggles. And this was not understood for a long time, but it turns out to reflect the chemical and structural information in aluminum. And it's a kind of signature of the metal. If you could only decipher it, you see it's wiggly. There are two names associated with it, which I'll explain. They're called XAS and they're called XANES. And the question is, why are they different? What's going on? So to be continued. So what's our theory? The theory that we're going to discuss is what's called a Green's function theory. We don't use quantum mechanics in the traditional wave function sense. So no wave functions. I don't know if you like that or not, but the problem with wave functions is that there are too many of them. And if you try to calculate X-ray absorption by this famous Fermi-Golden rule, you see that you have to sum over all the final states of the system, this aluminum, calculate all of those energies and then calculate all the dipole matrix elements and sum them all up, it's just computationally too demanding to be practical, at least with these broad energy ranges that we're talking about. So the miracle is that you can rewrite this Fermi golden rule in terms of a single equation that's summarized down here. It's basically an integral over the Green's function. The Green's function is represented in the Feynman diagram by this green line that goes from the point where the X-ray was absorbed and then back again to the initial state, which is a deep core state in the atom. So that's really simple. And somehow all of the sums are implicit in this beautiful formula. Mathematically, the Green's function is given by this formula. It's called a resolvent, and it involves a Hamiltonian, which has the deep core hole potential where the X-ray was absorbed, and something called a self-energy, which reflects the relaxation and many body effects as the photoelectron goes out of the material. So this is complex valued as a real and imaginary part, unlike density functional theory, which uses a real exchange correlation potential. So sorry, folks, but DFT has to be abandoned when talking about X-ray absorption theory, which is what we will do. So this is our game, the Green's function theory of X-ray spectroscopy. If you want references, I'm going to give two. There's a book that's devoted to this so-called real space multiple scattering theory, which is what we use, sometimes called real space KKR. That stands for Coringa, Kohn, Rostocker. And as you can see, there's a reference to a reviews of modern physics paper by that I've done with Bob Albers at Los Alamos that really summarizes the theory. And I'm proud to say we made the cover of RMP. And basically, this picture shows what happens when you absorb an X-ray. You kick out a photoelectron, but then it bounces around. And if you calculate all possible ways that that electron can bounce, that's called real space multiple scattering theory. It's like a giant pinball game. You can basically calculate X-ray spectra. Okay, so just to summarize, what's a Green's function? You all know what a wave function is. A Green's function is actually quite similar mathematically. It's a solution of the Schrodinger equation to an inhomogeneous driving force, in this case, just the delta function. And it's what Feynman called the propagator, meaning it tells you how an electron is propagated from one point, R, to another point, R prime, at an energy E. And if you can calculate this, you can really calculate a whole bunch of things. The beautiful thing about the formalism is that it incorporates all the many body effects in this propagation of the electron, because it's really a many body problem. There are lots of other electrons around, and they have to get out of the way as the photoelectron escapes the material. We use a famous theory due to Lars Hedin. It's called the GW approximation, in which the many body effects are represented in terms of a coupling to some density fluctuations called plasmons, and they're represented by the screened Coulomb potential W, which is the dotted line here, called the Hedin GW approximation. And if you want to know all about it, I strongly recommend this beautiful book on interacting electrons. It's by Richard Martin, Lucia Reining, and David Sepperly, just out a couple of years ago, and a superb summary of sort of the modern treatment of electron-electron interaction. Okay, but what's it do? That's what you want to know. You don't want to read about it in the future. So briefly, as I said, this self-energy is complex valued, meaning it has a real and imaginary part, unlike density functional theory. At low energies, it's perfectly okay to use a real, what's called density functional theory. It treats the many body effects in terms of a constant density-dependent exchange correlation potential. But as the photoelectron gains energy and goes into this wiggly part of the spectrum, the real part becomes larger, and an imaginary part kicks in. And what that means is that the photoelectron tends to have a very short mean free path. At low energies, the photoelectron can go very far into the material. So a lot of scattering. At high energies, there's only a limited amount of scattering because basically the material becomes very nearsighted. So at low energy, you can treat this so-called, now my mouse is gone, there it is. At low energies, you have a long mean free path. That's called X-ray absorption near edge structure. At high energies, the mean free path is short, and you have XAS. And the crossover is at the sort of excitation energy for the material. That's called the plasmon energy, and it's typically about 10 electron volts in the far ultraviolet. So for the optical region, DFT works great. If you're doing though high energy, then it doesn't work. Okay, well, it turns out that this multiple scattering theory, I'll just go over it briefly, consists of all possible ways that an electron can go from the origin where it's created and back again. So these paths are represented by Green's function. So this is the path where it just stays in the atom. This one starts at the atom, goes to a neighbor, is reflected, and goes back with another Green's function, and so on. And by summing all these up, it turns out that it looks very much like a geometrical series, and you can just calculate the matrix inverse of the bare Green's function and calculate this. This works great in the near edge. In fact, it's only practical in the near edge because the matrix dimensions get huge in the XAS regime. And this is basically computationally impractical. Okay, the other game is when there's only a limited number of scatterers, say near neighbors or next near neighbors. And this treatment is called the multiple scattering path expansion. Here, it's really computationally demanding because the dimensions get bigger and bigger as the energy is increased. Lmax is the maximum angular momentum, and this grows like the wave number of the photoelectron. So this is actually useless at high energies too because of the large matrix dimensions. And to simplify this, my collaborator, Bob Albers, and I invented a cute trick by writing a separable form of this Green's function. It's basically like cutting these Green's function lines in half, click, click, click. And if you do that, you can write this sum in terms of effective scattering amplitudes, which can be summed very quickly. They can be calculated individually. You can sum over all angular momentum at each vertex. So it's very efficient. Okay, in the end, we put these together in a code we call the FEFF code. F effective, this stands for the effective scattering amplitude in the theory. basically we calculate this Feynman diagram. And you see what's happening is that the photon, or X-ray, comes in, it excites an electron in the deep core and creates the photoelectron. That photoelectron goes out and creates plasmons and other excitations, but it also senses the core hole that's left behind. This is an attractive interaction. And although Einstein called it the photoelectric effect, I call it the photoelectron hole effect. Due to this, it's very important that you include this interaction. So the ingredients in the theory is you need to have a very good treatment of the electrons in the atom, a direct Fock code. You have to make the potential self-consistent. You need to calculate all these Green's functions. You need to put in a core hole. This is the, say, the 1s or 2p level, whatever. There's a whole bunch of edges. You need to put in a self-energy. You need to take into account thermal vibrations too. And finally, these many electron effects. So with a few very good graduate students, you can put together a code that can actually calculate these spectra. What are the results? Turns out the theory really works very well. Each of these multiple scattering paths can be written in terms of a path amplitude, FEFF, where our code comes from. There's a phase factor that has the near neighbor distance, or sorry, the total path distance, plus a little phase shift and a Debye Waller factor and some spherical factors. But the amazing thing is, if you calculate those wiggles in the XAS and do a Fourier transform, you get a result which is right on top of the experimental measurements. This was done, I believe, by Matt Newell. I'm not exactly sure of that. Anyway, the upshot is that it turns out that XAS is actually easier to calculate than to measure. This was in response to a statement by Hans Bethe that it was easier, usually, to measure X-ray spectra than to calculate it. But you need to know the structure to begin with. The beautiful thing, though, is that if you have a theory like this, you can estimate, and you have estimates of the distances, then you can use the technique as a fitting code and determine all the interatomic distances and coordination numbers of the material that you're interested in. So XAS is an X-ray microscope. And you only need a few paths to do it, in this case, 15. Okay, furthermore, it turns out the theory gives us a nice way of interpreting the spectra in terms of what are called projected densities of states. Due to selection rules, a photoelectron emitted from a deep 1s orbital or K shell gives you an electron with an angular momentum 1, which is called the P density of state. And if we now compare, this is looking very close to the edge, the P DOS and the X-ray spectra, you see that there's a direct correspondence, except that the X-ray spectra is a little more broadened, and that's due to this imaginary part of the self-energy. And similarly, the X-ray emission spectra comes from the occupied part. And again, it's in one-to-one correspondence. So X-ray absorption spectra is really measuring the distribution of electrons in a given final state angular momentum. It's a nice way of thinking about the what you're measuring. Oops. There you go. Another beautiful thing about this formalism is that the energy in the Green's function is really just a parameter. There are no eigenvalues. And it's similar to the way we measure spectra in a laboratory. We just have a whole bunch of energy points. As a result, the theory is naturally can be naturally parallelized. And if you have a computer that has a whole bunch of chips in it, you can give each chip a different edge and calculate the whole spectra very quickly. Okay, so this is the end of part one. And,
so if people have questions, go ahead and type them into the chat. But I'll start off just so FEFF works through these multiple scattering paths, and so in that way, it's really a real space code. When you build your simulation cell, you're building a cluster of atoms around your absorbing atom. And I was wondering if maybe you could say a few words about what size cluster you need. How many atoms do you typically need to simulate the XAFS of a material?
Okay, excellent question. This is determined by that mean free path that I mentioned. And typically, it's several what are called shells of atoms. Typically, 150 atoms is enough to get all of the information that you can see in the experiment. As you saw with that platinum example, you only went out to about fourth shell or something like that. Anyway, typically 150 atoms is what you can see. And this illustrates the kind of nearsightedness of the technique. So it's both a local atomic number specific and real space description of a material, unlike other techniques where you need thousands and thousands of atoms.
Thanks. Looks like Jerry has a question.
Yeah, John, I was curious. This is something I ought to know the answer to, but I don't. And that is, did the full multiple scattering treatment start with that Ankudinov paper, or had there been a prehistory of people doing FMS type treatments with Green's functions for other reasons?
It was before Ankudinov. Actually, Patrick Lee wrote down this real space multiple scattering treatment early on, and there were several other developments that actually came out of the Bristol group. So Bill Shake, actually, there's a very beautiful paper by Bill Shake who really started everything. He showed the formal equivalence between a real space KKR and the K-space KKR, which Walter Cohn developed. So I would say it's Bill Shake in the history. He just recognized that you could do the sum either way.
Great, thanks.
We could put the paper in the chat, or they can write to me, but it's William Shake, S-C-H-A-I-C-A.
Great. So Eric Shirley had asked, could you comment on the near edge where the mean free path gets longer?
The near edge, yes. In the near edge, it's sort of essential to do this summation by the matrix inverse technique, since that automatically builds in all possible scatterings through all orders. You can't quite do it in K-space because the core hole breaks the symmetry. So you have to do an impurity treatment if you do it in K-space. So I hope that answers the question. It's not quite K-space because it's a symmetry broken K-space and impurity potential, or do the matrix inverse. The matrix inverse works quite well because you only need a few hundred atoms for convergence. So that's practical in modern computers. And you can do that matrix inverse with Lanczos, or we use upper lower decomposition and standard linear algebra packages.
Great. And Matthew Marcus, you want to ask your question?
Yeah, I was wondering, in the XANES calculations, of course, you have chemical shifts due to valence. And does that get captured properly? Like, for instance, if you consider a mixed valence system and you do the XANES on the atoms at different valences, they come out shifted by the right amounts.
Oh, we have some approximations in there. You might argue with our calculation. I think it's tricky to get just right. So
at least at least you get somewhere near.
well, we try. Yeah, that's a technical issue. I think there are no really good ways of nailing it, although people claim they can. So, but no, you have to pay attention to the different atoms that are sort of chemically have chemically different environments.
Right, which means that the code, which means the code has to figure out what the environment is, has to figure out the ground state.
Oh no, the code that is separately done for each unique potential. So you have to pay attention.
Right, I realize that you have to give a different IPOT for the different species.
So anyway, let's defer that question. It's a little technical.
Okay.
If it's important, then we have to sometimes pay special attention to this. It's a good question.
Great. Well, if you want to continue, John.
Okay. All right. So the second part, I was going to discuss the relation between this real space multiple scattering approach or real space Green's function approach to other kinds of spectroscopies. One is called NRIXS, or non-resonant inelastic X-ray scattering. It's work that we also did with Jerry Seidler. And physically, what we recognize is that a lot of these spectra are related to what they call in physics the dynamic structure factor, S of Q and omega. S is the structure factor, Q is the momentum transfer, and omega is the photon energy. And what you realize in just looking at the formulas is that the formula is exactly the same as X-ray absorption, except that the transition operator, which in the X-ray absorption case is just the dipole term, epsilon dot r, becomes an exponential e to the iq dot r, because it reflects the momentum being transferred in the process. So if you write the Fermi's golden rule for S of Q and omega, you get a golden rule-like formula with the transition matrix in here. But that's very easy to rewrite with the Green's function. So you see it's very similar. And unlike the XAS, you don't have the selection rules allow for all possible ending momentum to come in. These are the matrix, transition matrix elements. And this is the projected density of states in a given angular momentum final state. So you can decompose the spectra and the Q dependent. So these plots actually show our comparison between our theory, which is this real space Green's function theory, experiment, see the pretty good correspondence, and something called the beta saltpeter equation. This is a more accurate theory. It's actually work done by John Vinson and Eric Shirley that calculates it. And the agreements, well, it's pretty good. So this enables us to see the momentum transfer dependence, which is also very useful, as opposed to X-ray absorption, which is like a long wavelength limit. How about Compton profile? A Compton profile measures a momentum density, and Compton was actually one of the first techniques where they realized the fermion nature of the electron. And again, the FEFF code turns out to be really in good agreement with this KKR approach that you mentioned before, right on top of it for various materials. And this, I must say, this is also very useful in what you might call an X-ray thermometer at high temperature, because this edge broadens with temperature. And it's a way of determining the internal temperature many, many thousands of degrees Kelvin. And I think you can see some of our people here, especially Gary and a former graduate student, Brian Matherin, who did this beautiful work. Okay, there's another very interesting technique that's used these days. It's called resonant inelastic X-ray scattering. And it's beautiful because it doesn't have this core hole broadening, which can actually blur out some of the phenomena. So this technique is actually used to determine excitation energies. The theory is kind of a mess. Well, excuse me, it's a beautiful theory. All due respect to our heroes, Chalmers and Heisenberg, but this is a sum over states theory. So as I said in the beginning, this is to be avoided. It's computationally difficult to do all these sums. And this has lots of extra terms. They're called interference terms. If you neglect that interference, it turns out that you can rewrite this in terms of X-ray absorption, X-ray emission, I think I mentioned that before too, the occupied part, and then this denominator, which is resonant. And this is sort of good enough. As you can see, the agreement between theory and experiment is, I think, acceptable. Acceptable at a fingerprint level to determine what the excitations are. So this is work of Josh Gass and Alexei Soininen and Peter Glatzel. Okay, recently, it turns out that all of these calculations have been done for all the materials in the so-called materials project database. It's about 100,000 materials, and it also comes with input files for FEFF. All the structure in these materials is calculated by the VAST code and is available. So this is an excellent starting point for any calculations that you have for all kinds of materials. This is an example of the copper spectrum, which a lot of you recognize. And I have a link in my talk to the materials project database. Okay, more recently, we have extended this database to include all of the optical constants, including index of refraction and reflectivity, over the full range from, again, the UV visible to hard X-rays. This is silver, for example, and you can see we have all the edges, and it's a reasonable description. Now you might wonder what the heck's going on here. At low energies, you have to include a phenomenological Drude term to account for the conductivity of an atom. And this calculation is done automatically with a new computational technique that manages all these calculations. It's called Corvus, so-called intelligent workflow manager. And I think I can try to click on this periodic table of optical constants, show off. I hope I can go fast. Here we go. Let's click on copper. Ah, there we are. Okay, so clicking on this gives you the various things. Turns out this is dynamic, so I can look in very closely, and you can see the fine structure. So really quite nice. Now I hope I can get back. Oh, amazing. Okay, so moving on to the third part of the talk, and we'll have the question period in just a minute. We had a little bit of phenomenology in our original calculations some of the terms like the Debye Waller factors were approximate, but it turns out you can calculate all of those parameters theoretically, and that's described in this review in Rendu in 2009. So this again is our sort of state of the art theory 10 years ago. It's not the latest, but I'll just briefly go into what we do. One, we have a new code. Actually, this new code is pretty recent, 2017, and it goes up to atomic numbers 138. So we can even do things like Seaborgian, and it's fully relativistic. So this is our atomic code now. So if you want to do things out of this world, yeah, go to the super heavies. How do we do the core hole? You can either, when you put a core hole in the material, when the X-ray comes in, all the other electrons move toward it to screen it. And that can be treated either by the so-called final state rule. It calculates the final state potentials, including screening, or something called the random phase approximation. They're pretty close together, but they screen the core hole and reduce its magnitude by about a half from the unscreened value. So we have to do a very good treatment of the core hole. That turns to be ought to be essential in many materials. This self-energy we calculate by using what's called a plasmon-fold approximation, but you need the loss function to do that. And anyway, when you have it, you get these curves that I showed for the real and imaginary part, and they work quite well. In fact, they work a little better than our default plasmon-fold approximation from Houdini. The Debye Waller factors are also calculated by ad initio, and here we need to know the phonon density of states. We call it rho of omega. This is the Bose-Einstein occupation numbers. The hyperbolic cotangent is essentially n plus a half h bar omega. And this you might call a many-pole model for phonons. You don't need all the phonons, you just need the sum over these, which is, so it's very efficient. And we get the dynamical matrix in this calculation from a DFT code called Evan. Okay, so what does this do? We did a comparison with the DFT code. It's called Paratech. It's a code by Delphine Cabaret and others in Paris. And we wanted to compare DFT, this is our standard theory, with the FEFF code that has the self-energy, and experiments the red crosses. And you see what happens is that the self-energy accounts for this kind of systematic deviation from DFT to green as one goes up in energy. And if you don't have it, you get rubbish, except very close to the edge. So self-energy is really crucial. Okay, here we are. Questions for this part?
So John, we have a couple questions about Compton profiles. The first is that is the simulation of Compton profiles part of the FEFF package?
Yeah. As an example, even the new FEFF 10, you go into it should be there.
And sorry, could everyone mute? And then also on Comptons, are you aware or have you considered studying Compton profiles of highly doped semiconductors? The idea being that perhaps you can get a high temperature compared to the effective carrier Fermi level, I believe.
Sounds fascinating, but the brief answer is we've mostly concentrated on the theory, and other people have then used it and asked us questions. You know, but I certainly haven't played with this. Actually, it was Brian Mattern who did a lot of the work, and with Terry I'm not the right person to ask.
Okay, well, since there don't appear to be other questions, why don't you continue?
Okay. How am I doing on time?
It's 12:45 or 9:45 for you.
Okay, I'll finish in about 10. So here we go. So, okay, we're never happy, of course, with the theory. It takes a long time to polish things. But it turns out that the theory that I've discussed is a pretty good theory, but it's an effective one-electron theory. It treats the photoelectron quite well in the presence of the core hole, but it really ignores the excitations. And it turns out that when one measures this fine structure and does a Fourier transform so you can see these shells, the theory usually overestimates the fine structure. And that's because the theory neglects these intrinsic losses, which sort of steal spectral weight out of the photoelectron. And it's like inelastic losses or multi-electron excitations. So when you suddenly turn on a core hole, you can also create density fluctuations that steal weight. Well, the beautiful thing is that you can add these to our theory very simply by treating these processes as independent. And then all you have to do is add a convolution between what you calculated already. This is the photoelectron or quasi-particle X-ray absorption, and then the core hole spectral function that builds in all of these excitations. We use what's called a Cumulant Green's function for that approach. I don't have time to go into it, but it's a very beautiful formalism for building in excitations, originally written down by our hero Lev Landau in 1944, and I strongly recommend it. Please see the Reining, Martin Reining separately book for details. And there's a recent review by Sky Zhao and others in J10 2015. Okay, so what happens? So if you look closely at materials like transition metal oxides and the near edge, what you see is that the single particle theory, like the FEFF code, has too much strength at the edge compared to experiment. And it misses these kind of early peaks. They're called satellites. But the convolution formula builds it in. And this was done by Calandra and company in Paris. And they represented these excitation spectra with the XPS spectra. Okay, we did a little better theory in which we included all the possible excitations, both the extrinsic, intrinsic from the core hole, and then it turns out you need to add these interference terms because you have to add amplitude in quantum theory, and you also get a convolution. Okay, so in the end, when you calculate this with the cumulant and add them all together, you basically fix up all of these missing spectral pieces and get a reasonable agreement. Okay, finally, I'll spend a little bit of time on the high temperature extensions. This was done by our graduate student, Sun Tan. This should read 2021. I don't know how this got in here. So we wanted to generalize the FEFF code up to warm dense matter temperatures. This is the sort of the temperature in the outer part of the sun or the interior of planets, or the temperatures that you can get when you hit a material with an X-ray electron laser. Okay, when you go up in temperature to very high temperatures, what happens is that the edge actually gets lower, and that's because the Fermi function starts at lower energies, and you get what's called continuum lowering. That can be calculated by this Sommerfeld expansion. And it works quite well, even up to 10 to the 5th Kelvin. You have to modify the exchange correlation potential. That works quite well up to maybe 1/3 of the Fermi temperature. But at very high temperatures, it turns out that exchange becomes very small and correlation takes over. This is actually calculated from first principles using Galitsky-Migdal Cumulant Green function. The other interesting thing at very high temperatures is that the real part of the self-energy gets smaller and smaller. This is because the correlation, the exchange part goes away, but correlation gets larger and larger, so the imaginary part grows. And as a result, phenomena like band structure and band gaps get all smeared and blurred. All materials become metallic, and it's actually easier to calculate than at low temperature. There are kind of two effects when you heat things up with a free electron laser. The electrons, the electron go to very high temperature, and you have to treat the electrons and the lattice temperature separately. They're often out of equilibrium. When the electrons are heated up, you get this continuing lowering, and you see these formerly occupied states. When the lattice temperature grows, you basically blur out these wiggles, and you get vibrational damping. So you have to have a code that does both. And as time goes on, what you see is initially you heat the electrons, and then they slowly exchange energy with each other and equilibrate. But you can do a time-resolved X-ray absorption experiment and follow the dynamic with an X-ray free electron laser, so it doesn't pump probe experiments. So this is a very important modern technique. I'm at the end now. I just want to mention there are some new software initiatives that aim to develop new codes. One is this collaboration we have at SLAC. It's called PRIMES. It's a new theory institute for materials and energy spectroscopies. We have a new code. It's the FEFF10 code, and it has a GUI plus this Corvus intelligent workflow manager. There's a related initiative at PNNL, which is more devoted to quantum chemistry applications, but we also use the Cumulant there. And if anyone is interested in the updated FEFF10 code, here's the link. I think John Vincent's going to put it in the chat. And that brings me to the end. So let me give some conclusions. We've developed a real space Green's function theory for X-ray and related spectra. It's now pretty well developed. It's fairly accurate and broadly applicable throughout the periodic table. What I want to emphasize is that this energy-dependent self-energy and vibrations are essential. So it's different from DFT. And it's also important to include this cumulant spectral function if you want to account for the last 10%, the inelastic losses and overlap factor to get agreement between XAS and theory and experiment. And we have this FEFF10 code for various spectra. All of these are available as examples in FEFF10, except for optons. That requires Corvus to do. Finally, we have this Corvus workflow tool for complex calculations that combine multiple codes. So this is a list of people that contributed to the code, taken when everyone was here. They weren't all there simultaneously. I listed a few there. There were many others. I apologize if I've missed you, but I appreciate we've really benefited from help of many people around the world. And especially support from the DOE Office of Science, Theoretical Condensed Matter Physics Program, and Chemical Sciences Program. And that's all. So I will sit there and take further.
All right, thank you very much, John. To start, I was going to ask, so you showed some results with the effective shakeup. Is that integrated into FEFF10 or Corvus?
Not really yet, but it's being incorporated. We have something called a many-body convolution tool in there, but the input to it is maybe not always there, but it's coming soon. So if you have the ingredients, it can be put in, but it's I would say it's imperfectly integrated at the moment, but it's on its way.
Okay, and following up
I just
on
have
that.
a quick comment.
Oh, Josh, yeah.
Sorry. It is integrated into Corvus, but you do need the real-time version of Siesta in order to calculate the spectral function.
Thanks, Josh.
Thank you. Yeah, that's a good reason to start using Corvus. It makes FEFF much more powerful when combined with other code.
All right, and then Eric Shirley had a question. Eric, if you can.
John, would you like me to ask the question?
Yeah, go for it.
I'm unmuted. Can I ask it? Okay. John, wonderful talk. Thank you for giving that. Really enjoyed it. Your Kramers-Heisenberg formula that you use, that energy convolution that you have?
Yes.
Strictly speaking, is that exactly the same as the Kramers-Heisenberg formula, or are there some minor approximations that it makes?
Oh, we neglect the interference terms. If you expand it out, you can see you'll get that by sort of staring at it and keeping the dominant term. It's a
but
nice
you are
formula.
still including. Are you still including interferences between degenerate states?
At the moment, I cannot remember precisely how we derived it. We wrote out everything and crossed out a bunch of terms, cross terms, and that's what popped out. And when we first developed it, or at least what I wrote down, was just the convolution of the density of states, occupied and unoccupied. And then Josh realized that, hey, we have the matrix elements too. So that's basically how that evolved. And it's really explained in detail in that paper, but I can't remember the details at this second.
Okay, thank you.
Okay, there is also a question, are you able to calculate satellites in XPS using FEFF?
Well, you need this spectral function, which, as Josh says, is calculated with Corvus. And it's basically it's calculated with RT-Siesta. So basically what we do is we turn on a core hole at time t equals 0, and then time evolve the electron density. Basically, that's going to create density fluctuations, and they will oscillate, as you can imagine, at the sort of natural frequencies in the material. If you Fourier transform that, then you get the excitation spectrum that goes into the convolution. But it's a Corvus workflow that has to be done, and you need this RT-Siesta real-time. Siesta is a DFT code, but it's basically a time evolution code. So it goes beyond what's in FEFF, but then we just run the convolution where you put in the spectral function X post facto, and bingo, the excitations go in.